In this last part of the linear algebra review, we'll talk about eigenvalues and eigenvectors. And this is actually a topic that we will use when it comes to dynamics and understanding the dynamics of a system. Eigenvalues and eigenvectors actually give us a lot about the behavior of a dynamical system. So just from the linear algebra point of view, if we have a square matrix A that has dimension n, then there is a value, a scalar number this lambda that actually could be complex. Right here I've written it as a real number, but it could be complex. And here this v, I've written it as a real number, but it also could be complex. And it's a special value and vector v such that a multiplied by that vector is the same thing as lambda, a number, times that vector. And so the idea of this is that v is a special direction in which a changes v into a different scaled version of itself. So v maps into v only the fact that it is scaled by the value lambda. If lambda is negative, then it flips v. If it's less than 1, then it shrinks v. If it's more than 1, then it lengthens the length of the v vector. So we call v the eigenvector and lambda is the eigenvalue. And so how do we find these? We actually just solve this equation. So if we move lambda v to the other side and set that equal to 0, we get this equation here, which says that the vector v multiplies this matrix, which is A minus lambda times the identity matrix, and makes it 0. And so if you're going back to some of our definitions, this is actually the null space. V is in the null space of the matrix A minus lambda I. And so for this to be singular, for A minus lambda I to be singular, we're picking a lambda such that this has diminished rank. Or another way of saying that is that such that this matrix has determinant equal to 0. And the determinant ends up being a polynomial. It's called the characteristic polynomial. And it is an nth order polynomial. And we can solve this nth order polynomial in order to find the values of lambda for which A minus lambda I is singular. All of this is talking about right eigenvalues simply because we multiply v times a on the right-hand side. Similarly, we can talk about left eigenvectors. One of the consequences of eigenvalues and eigenvectors is that we can use it in order to diagonalize a matrix. And so the process of diagonalization is the idea that we can represent a matrix A. Now I'm looking down here at the bottom of the page. I can represent a matrix A in terms of a matrix V, and that's composed of some special vectors. And lambda here, this big lambda, this is a diagonal matrix, which means it's all zeros except there are elements that are possibly non-zero on the diagonal of that. And this comes directly from a consequence of the eigenvalue-eigenvector equations. So in fact, there are n eigenvalues that satisfy the characteristic polynomial that we derived on the previous slide. By combining all of these equations together and putting each one in here, so this comes from that equation, and this side also comes from that equation. This equation gets stuck in on both sides of this next equation. And so we build out essentially the matrix eigenvalue-eigenvector relationship. And what we see is a matrix A multiplied by what we're going to call this matrix V is equal to V multiplied by this diagonal matrix. And this diagonal matrix has all of the eigenvalues on its diagonal. And so this is the eigenvalue-eigenvector matrix equation. And so the important thing here is that V is the matrix of all of the eigenvectors as its columns. And so if there are n linearly independent eigenvectors, in this course we're pretty much going to assume that that's always going to be the case. There are some cases where that's not true. But if there are n linearly independent eigenvectors, this allows us to diagonalize A, and we just merely move this V to the other side by post-multiplying by V inverse. And that's how I get this equation here. And similarly, if you wanted to rearrange it, you could rearrange it in terms of the eigenvalue matrix lambda. And a similar thing can be derived for the left eigenvectors. A generalization of the diagonalization process is the notion of a similarity transformation. And a similarity transformation just says that a matrix B is similar to a matrix A if there's an invertible matrix T such that this pattern changes A into B. And so in this case, neither A or B needs to be diagonal. Diagonalization, however, is one case where we require, for example, B to be a diagonal matrix. And so one of the consequences of this, which makes sense in the context of our discussion on diagonalization, is that similar matrices have the same eigenvalues. And so we know that if we diagonalize A and we get lambda, that lambda is the diagonal matrix of all of the eigenvalues of A. And so inherently they automatically have the same eigenvalues. Some other interesting properties about eigenvalues is that the trace of A is equal to the sum of the eigenvalues, and the determinant of A is equal to the product of the eigenvalues. And a final tool that you won't need in this course, but is an interesting way to complete everything that we've just talked about, is to talk about singular value decomposition. SVD underlies quite a bit of many of the interesting things that you deal with on a daily basis that you don't know about. And this is a way of generalizing eigenvalue, eigenvector decomposition, or essentially diagonalization, but doing that for rectangular matrices. And so when A is no longer a square matrix and it's a rectangular matrix, we can do a similar process where instead of finding eigenvalues, we find singular values. And we also find, instead of a single matrix, V, we find two matrices that really act as kind of left and right eigenvectors together, and that's what composes A. This goes beyond what we need in this course, but if you're curious, you can certainly take a look at this more deeply.